Today's training topic is testing submersible motors with meters and Meggers. More importantly, not only am I going to show you how to test a motor with a multimeter or a megometer, more importantly is how to understand what it's telling us. The biggest challenge that I think we face today, and this is just an opinion, but I personally believe that there's been a big gap in education over the last 20, 30 years. Ever since this industry went to field scrapping versus repair, a lot of information has gotten away from us. And quite frankly, there's a lot of contractors out there that didn't get the type of education that daddy and granddaddy got. And so they're starving for this stuff. And I would venture to say that probably less than 50% of the contractors out there would understand what these resistance values are telling them. And it's important to know that because now you know whether that motor is shorted or whether it had an open winding, and you kind of determine the root cause failure that way. And I think the biggest challenge is just taking the mystery out of it so that they understand these resistance values. They're published, so they're easy to get. And once you understand what this meter's telling you, you'll get a lot of good use out of it. When we look at multimeters first, all right, understand that multimeters measure resistance, and in so doing, they will express that resistance or they'll display it in what's called ohms. If there's no resistance at all, your meter will display 0 ohms, all right? So 0 ohms would be equivalent to no resistance at all. 0 ohms is also referred to as infinity, and all multimeters are going to have a infinity display, but it can be displayed one of two ways. So also be aware of how your multimeter displays infinity. Many of them simply display it as an OL, open lead. Other multimeters will display infinity as simply a 1. And so again, understand which way your meter is working so that you know what display represents infinity. There are two types of multimeters, two basic types. The one on your left is referred to as an analog meter. That's been around a long, long time. Commonly used 20, 30 years ago, still used today. But the thing about an analog meter that you want to be aware of is that there's a dial at the bottom of it that you would want to adjust before you take your measurements. The way I've done this in the past is I've always set it at the highest setting. And then I'll work my way down from there to get a more accurate reading, but I start at the highest setting. There's also a dial right in the center of that analog meter that will enable you to zero out the needle. These are important things that need to be done before this meter is used each and every time. You want to adjust the scale and zero it out. The digital meters, on the other hand, they don't have a need for either one of those. They've got auto ranging features to them, and there is no need to zero those out. So again, it doesn't matter whether it's an analog meter or a digital meter. We need to understand what they're going to be telling us. And with a multimeter, there's a lot of things that you can determine about a motor. You can determine if a motor has a short. You can determine whether it has an open winding. There's this thing called mixed leads out there we'll touch on. You can identify leads with a multimeter. And of course, we can determine whether a motor is grounded or not with a multimeter. Anytime you're going to use a meter to test a motor, always be sure that you have no power running to that motor. So a lot of times I like to see the power cut off even at the pressure switch because these meters are going to display ohms without any power applied. So when we talk about the last thing before we're going to use this meter is make sure it has functionality. Cross your two probes, cross your red and black probes, and when you do that, you should get that infinity reading displayed in your meter. Make sure your meter's functional. When we talk about submersible motors, there's a couple of types of those as well. One is simply referred to as a 2-wire motor. A 2-wire motor will have 3 leads coming off the motor itself. We'll call 2 blacks and a green. So we'll simply refer to those as lead A and lead B and the green ground. The 3-wire motor, on the other hand, there's 4 wires coming off that motor lead. There's a red one, and that's your start winding. There's a black one, which is your run winding. There's a yellow, which is common, and of course the green is ground. Now, understand, this is common across the industry. This is not exclusive to a Flint Walling motor. Any other motor, these color-coordinated leads will represent the same thing, such as start, run, and windings. Let's go ahead and do some testing here. With a multimeter, we're going to look for a short, an open winding, mixed leads, lead identification. With any of these shorts, open windings, mixed leads, lead identification, on every one of these tests, the way that we're going to measure with our multimeter is we're going to go each lead to lead, all right? So on a 2-wire motor, that's done one time. You're going to go lead A to lead B, both black. That's it. But on a 3-wire motor, you're going to go red to black, red to yellow, yellow to black, so on and so forth. Each lead to lead. And when you do that, you will get some resistance of some type, all right, in your meter. So it's going to show you some resistance. Now, therein lies the big question as to, what should that resistance be? How do I know whether this is a good reading or a bad reading? Any pump company that manufactures a motor, Flint Walling included, puts out in our case, it's called a motor application guide. All other pump companies that manufacture motors, they also have these type of guides. And in these type of guides is where you're going to find these resistance values. So for example, this is a centerfold of our particular guide. All right, I want to show you how you know what the resistance values should be. First of all, over on the far left-hand side is motor type. All right, so we first need to decide, are we testing a 2-wire motor or a 3-wire motor? Once that determination's been made, now we got to go with what horsepower is it, all right? What horsepower? So once you have the motor type and the horsepower identified, if you come all the way across that chart, you'll see winding resistance over there, and those are the numbers that are published, and those are the numbers you're looking for in your multimeter. So let's just suppose, by example, we select a 2-wire motor. Let's make it a 1.5 horses, all right? If you circle the 2-wire and the 1.5 horses and you scroll across over there to winding resistance, right there's what you should be showing in that multimeter. When you put those probes on the black and black wire, you should be coming in at 1.6 to 2 ohms, all right? That's what you should be coming in at. On a 3-wire motor, there's going to be 3 leads involved, right? 3 leads involved. So let's go the same way, 3-wire motor, 1.5 horses. And then when we scroll across, we're going to see in the case of a 3-wire motor, there's actually 2 published values, all right? 2 published values. And again, this is very, very common amongst motor manufacturers. So in this case, we have 2 published values. One's referred to as an M, the other one referred to as an A value. Both of those are identified in the bottom right-hand side of this chart. But if you look at it closely, what the M value is, that's your yellow to black wire. And that should come in at 1.7 to 2.2 ohms. Your A value is your yellow to red, and that should come in at 7.8 to 9.6. So again, that's going to be on a 3-wire motor, all right? So with that all said, here's something that is important for you to know. I think if you remember this, it's going to go a long way, particularly if you ever want to identify leads. So let's look at it this way. We talked about the yellow and black. On a 3-wire motor, that should come in at 1.7 to 2.2 ohms, all right? So one way we can refer to that is that is the lowest value. That's the lowest value. We go to the yellow and red, that's supposed to come in at 7.8 to 9.6. So we could refer to that as the intermediate value. And then there is the start winding and the run winding together. That's your red and black wire. There is no published value for that. So how do you know what that should be? The answer is quite simple. If you want to know what the value of that black and red wire should be, all you need to do is add your lowest value to your intermediate value, and that's going to give you your highest value. With that information right there, if I knew that the yellow and black were my lowest, and the yellow and red were my intermediate, and the red and black were my highest, if you gave me a motor that had nothing but black leads coming out, I don't care, all black, with this test, in a few minutes, I'll tell you which one should be red, which one should be yellow, which one should be black, based on this information that we have on the screen right now. So that's an important thing to remember, that the lowest value added to the intermediate value ought to be awfully close. I'm not saying it has to be spot on, but if you have a low value of 2 and an intermediate value of 8, and you have a high value of 10.1, that's enough to make sense to me. So again, lowest added to the intermediate equals the highest value. So let's do some testing here. Helping us to test some motors today is Luke McLemore. Luke is Flint Walling's regional sales manager for the Midwest and the upper Northeast portion of the United States. We have several motors in here with varying problems, and what we're going to do is show you what type of readings you'll see so that you can diagnose these varying problems in the field. So with that, we're starting off with a 1/2 horsepower, 3-wire, 230 volt submersible pump motor. In testing this, I would like you to put your probes on your yellow and black leads This should be your lowest value. This should come in between 4.1 and 5.3.
Perfect. Dan, I'm getting 4.6.
4.6. Hey, that's within range. That's perfect. All right, that's perfect. That test pass. Next, we're going to check for intermediate values, which will be the yellow and red wires. The published values for the yellow and red wires should come in at 18 to 21.9.
Dan, I'm gonna 3.9 here, Dan.
3.9.
Yes, sir.
So that's not good. Supposed to be at 7.8 to 9.6. So in this case, I am actually coming in lower than the resistance values that are published. And I want to talk to you about how you can remember this, all right? Anytime you come in lower than the published values, I want you to think of it this way. You got two stools here? No, you just got one, but I'm going to bring a second one in, and guess what? It's shorter than the first one. It's lower than the first one. So anytime you have an actual value that is below published values, it's lower, that indicates a short, period. It's a short. We could take it one step further and identify actually where that short's at. So if it's lower than range, let's look at that. Let's go back to the test that we just did, all right? The intermediate range failed. What was that? Yellow to red. And I'm going to tell you something. Anytime one of those top two values fail, the bottom one will always fail. So anytime you have a failure at the top, you can terminate your test at that point, because that bottom one, that red and black, that high value, that will always fail. However, if you want to identify, in this case, where that short's at, we know that the yellow to red failed. We know that the red to black failed. So the commonality there is the red wire, right? So obviously the short would be in the red wire. When the yellow and black were together, they worked just fine. It was only when they paired with the red wire that they failed. So that's a short. Let's do another one. All right, now we're going to test yet another half horsepower 230 volt motor to see if we can determine the cause of failure with this one. We're going to perform the same exact test. And again, we're going to start off with what we would refer to as the lowest values for resistance, which is our black and yellow wire. And again, on that black and yellow, that half 230 volt should be coming in at 4.1 to 5.3 ohms. So Luke, what are you getting there with the yellow and black?
Ooh, Dan, I'm getting 20.2.
Oh, 20.2.
20.2, no, 20.3.
So in this case, your readings, your resistance values are coming in higher than the published values. If you recall in the previous test, we came in lower, which was an indication of a short. So anytime you come in higher, what's that going to be an indication of? Well, if you raise that window up higher, what are you doing? Well, you're opening it, right? You're opening it. So there's your tie-in. Anytime the resistance values are higher than published, think of opening a window. It's an open winding. That's what that indicates, is an open winding. And again, if we wanted to know where that open winding was at, look at the two categories that failed. Well, the red and black failed, and so did the yellow and black fail, so the obvious open winding is going to be in the black wire. All right, so if anytime you come in within range, that's good, but if you come in higher than published values, that indicates an open winding. Let's move to this next one called mixed leads. Now, I'm going to tell you that this is not the most common issue or problem that you'll find when testing a motor, but it does exist, and it's referred to as mixed leads. And so when we look at mixed leads, how do we know what kind of resistance values we're going to get in that situation? Well, let's look and see. Luke, let's go ahead and do another motor yet. So let's put the probes on your yellow and black, which should be, once again, the lowest values. What type of resistance are you getting there?
20.3, Dan.
20.3. 20.3. That should be coming in at 4.1 to 5.3. So in this case, you have resistance values coming in higher than those published values. So what I want you to do next is go ahead and check that yellow and red wire, Luke, see what we got there.
Yellow and red?
Yellow and red.
All right, Dan, the yellow and red are giving me a reading of 4.9.
4.9, and that should be the intermediate value that comes in at somewhere between 18 and 21, 22. So in this case, you have a resistance value that's coming in lower than published. So both of those failed. The difference in the failure there is that one come in higher and one come in lower than published values. Anytime that happens, that is a prime indication of a mixed lead. All right, that's what that's going to be. It's going to be a mixed lead. Now, when we talk about how could a mixed lead, how could that happen? You know, what could cause that? I suppose at the manufacturing level, if the manufacturer did not wire the lead socket properly in the motor, so that when you bring your motor lead down on top of it, those wires are not lined up properly, therein lies a mixed lead situation. That could never happen at Flint Walling. There's way too many tests. That would never be able to get out of the building. And I'm not suggesting that other pump companies would, you know, but look, that's one area where that could happen. More than likely where that's going to take place is in the splice, right? That's your underwater splice. It's 4 feet above the motor. And again, oftentimes when a pump gets replaced, those power cables aren't all vibrantly colored like they are brand new on the spool. They get faded, they get dirty, they get ugly. You don't even know what colors they are sometimes. Therein lies a chance to have a risk of hooking the wires. If you got a yellow wire hooked to a red wire and a black wire hooked to a yellow wire, and it's not going to work. That's called mixed leads. You'll get higher resistance values and lower. Okay, now we got one more to go. All right, and again, these are all things that a multimeter can tell us if we understand what it's telling us. This last one that we're going to do is what's called a ground. All right, it's commonly, probably one of the most common tests ran on a pump motor. So this is the only time that when we take our measurements, we're going to go each lead to ground. On this motor, what we're going to do is check to see if the motor is grounded or not. Again, the process that we're going to use here is we're going to take each lead to ground. If there is absolutely no resistance across those leads to ground, then that motor is not grounded. I'm not saying it's a good motor, but I would say it's not a grounded motor. On the other hand, if you get resistance, any resistance at all, across each of those leads to ground, that is an indication of a grounded motor. So Luke, let's go ahead and start off there with that black lead to ground, and let me know, are you getting any resistance?
I am, 0.1, there's some.
All right, how about yellow?
Same.
Red?
Three for three.
Okay. So in this case, we're showing resistance, and we're actually showing resistance across all those leads to ground, which is not uncommon. If you get resistance, any at all, it's a grounded motor. That's black and white. That's a very easy test to run. It's black and white. No resistance, no ground. Any resistance, even small, indicates a ground. I had a contractor come up to me. I don't know if I was just starting this class or just finishing this class one day. And he said to me, Mr. Painter, he said, I pulled a pump and a motor out of the well earlier this week, and that daggone thing was grounded on all 3 legs. That's what he told me. He said it was grounded on all 3 legs. Almost like he was really trying to emphasize, dude, this was really, really grounded, right? But I think as most of us know, when it comes to testing a motor for a ground, what he told us was the rule, not the exception. More than likely, if you have any resistance across one of those leads to ground, more than likely, you're going to have all resistance off every one of those leads to ground. I thought there might be a day that I'd outlive this, but apparently not. The very first submersible motors ever sold, 20, 30, 40 years ago, they did not have a ground wire on, right? And they're still in today. So in that case, if you ever have to test one of those for ground and it doesn't have a ground wire, you need to create a ground, right? If that motor's still in the well and they have a steel cased well, you can scratch or etch the side of that steel case and get yourself a nice ground. And then you can test and see whether that motor is grounded or not. If you've got that motor out of the well and you want to test to see if it's grounded and it doesn't have a ground wire, use the side shell of the motor. Again, just get yourself an etched portion of that side shell motor and get a nice ground, and you can tell if it's grounded or not. So the last one here is if there's no resistance at all, there is no ground, and any resistance equals a ground. So the takeaways: anytime you are coming within range of the published values. That's always good. That's always good, as long as you're within the published range of those values. If you come in lower, that's going to be an indication of a short. If you come in higher, that indicates an open winding. So think of it as the open window and the short stool. If you come in both ways, higher and lower, that's mixed leads. And then that math equation, I can't emphasize that enough. That math equation, knowing that is a very, very good piece of information to hang on to. Probably the greatest benefit that one would get out of using a multimeter is knowing what the root cause failure is. The last thing we want to do is pull something out, replace it, not know why we're replacing it, because oftentimes you end up with the same problem. And so identifying that root cause up front before the replacement comes in can save a lot of time, money, and frustration, and this meter will go a long way to keeping us straight on that path. Now we're going to switch to megometers. Undoubtedly, there are a significant higher percentage of contractors and installers that possess a multimeter than those that possess a megometer. And sometimes people ask, well, do I really need one? Well, if you've been in business for 20 years and you've never had one, that's going to be a hard argument for me to try to win, so I'm not even going to go there. But I will tell you this, if you sell variable frequency drives, VFDs as they're commonly referred to, if you sell those, and that's part of what you do, a megometer investment would be very, very important, because these drives, they have voltage spikes, and sometimes that can burn right through a wire or a cable that is not properly sized for the application. And a megometer is going to give you that information to be able to determine that or not on a variable frequency drive. In looking at megometers, all right, there's a big difference between megometers and multimeters. A multimeter measures in ohms. We talked about that earlier. But understand this, that a megometer is going to measure in megohms, all right? 1 megohm is equivalent to 1,000,000 ohms, all right? The only purpose that we have for a megometer in our industry, be it irrigation or water systems, when we talk about what does the Megger do, is it's going to test the condition of that power cable. All the insulation on your power cables, all right, all your wire, the condition of that insulation degrades over time. And you can get nicks and cracks and pinholes and things like that. So any nicks, thin insulation, it'll go right on down into the copper windings in the motor, which also has a thin film of insulation on those. And those also degrade over time. So again, with a megometer, it's going to evaluate the outer coating of your electrical cable. I saw this online one day and thought it was very, very good. So I'm not taking any credit for this, but if you want to understand how a Megger works, it can be better understood if you compare it to water flow, which we all understand that, right? You got a piece of pipe and you're going to put a pump on the end of it. And what that pump's going to do is it's going to shove water down through that piece of pipe, right? All right, so let's think of that piece of pipe as a copper wire that's got insulation wrapped around it. That's your insulated copper wire. We're going to put a pump on the end of that too. It's called a megometer, right? Think of it as a pump, because what that megometer is going to do that your multimeter couldn't is it's going to push a lot of current down through that electrical power cable. Look, this is going to put out 1,000 volts or more. It's going to really exploit that wire, which we want to do if we want to determine if it's in good condition or has these thin insulation pinholes or cracks. It's a non-destructive current, but it will exploit anything weak in that cable. So with a water pump, right, as you push water down through that pipe, we experience what we call friction or friction loss. That's very, very common in water flow. In megometers, you're looking for resistance. All right. So again, if you kind of look at it as compared with water flow, it makes it a little easier to understand, because if that pipe that has the pump hooked to it, if it ever sprung a leak, guess what? You're going to waste water. You're going to lose pressure. Well, same thing happens up here with the electrical cable. You get a thin spot in that, or you get a nick in it or a pinhole, you're going to have an electrical leak. And a megometer is going to pick this up. A megometer can almost tell you where a pump and motor may be in its whole life expectancy. And now to show you what we've been talking about with megometers, let's go to Ben over in the factory.
All right, thank you, Dan. Okay, so we're down here on our factory floor here in Kendallville, Indiana. We're standing in our 4-inch submersible manufacturing facility here. Back behind me is our end-of-line tester. What we're talking about today is testing motors. That's not the only thing we test here at the factory. If you've been on a tour, you've seen we check all of our motors, all of our pumps, every step along the way. If you haven't been here, get with your sales guy. We'd love to have you. We'd love to come see you here for a tour and some training. But today, we're gonna come over here and take a look at what we're doing at the end of the submersible line for our motors. Okay, so we're down here today, end-of-line tester here for our submersible motors. We're here with Shelby. Shelby, thanks for letting us come down here and do this. What we do here is we've got these tanks. We put the motors in here. They sit in this tank for 2 hours. Every motor we make sits in this tank for 2 hours under 100 pounds of pressure. What we're trying to do there is mimic similar conditions to what we might have with the pump installed in a well. So with that pressure, we're checking our welds, we're checking for leaks. But at the end of the process, what Shelby does is she comes over here and she uses a Megger, and we check everyone individually. So we are, so we're gonna use a Megger on these motors. Now, you've learned about what a multimeter does. So we know a multimeter is testing our winding resistance in the motors. A Megger, on the other hand, is going to check the insulation resistance. So we're gonna check that insulation resistance on the lead wires. We're gonna check it on the socket. That test is gonna go all the way down into the core of the motor. We're gonna even check the copper windings on the stator here with a Megger. The other major difference between a meter and a Megger is this thing's gonna use a whole lot more voltage. So we're gonna be checking these motors with 500 volts, yes. I believe. 500 volts today. So let's take a look and see how the magic happens here. Yeah, so right now what we're doing is we're just giving every single motor in here a quick spot check, making sure that we've got a healthy insulation resistance here. And now Shelby, when one is not good, what are you gonna see on your screen here?
When one is not good, it will not stop at one. So you'll see they'll flash up to a variant of different numbers, but as long as it goes back and stays on that one, it's good. If one were to fail, it would, let's see if I can get one to fail. It will read as 0, like that on the screen, meaning that water has probably gotten into the motor or the lead. But on a normal part, if it's not touching the metal at all and it just fails, it's gonna be probably water either in the stator or the lead. If it's in the lead, we can change out the leads and retest it. And if it's in the stator, we'll have to take it to our repair team to get fixed.
When would you want to run a Megger test? You know, most of our customers, most of our sales guys, you know, a meter is generally the go-to tool to use when you're looking for whether a motor is good or bad. The truth of the matter is, Meggers they're not as frequently used out in the field. Where they really come in handy, though, at least from my experience, is when you're looking at a VFD. You know, you could have a small break or just a small crack in the insulation that can't be picked up with the 12 volts that a multimeter is putting down there. But you can pick it up with a Megger, and the VFD is definitely going to pick it up. So where a Megger is most helpful is in situations like that, where say you've got a drive on the wall and it's throwing a short circuit. You get out your meter, you check, and you're not seeing any short. Put a Megger on it, and odds are it's probably going to show that you've got an issue.
So on this one, we're having this one not hit 0. It's changing to a couple different numbers. That means something probably electrical. So what we'll do is we will bend these down so we know which one's bad. And we'll mark it with our marker. so that when we take them out in our next step of the tanking process, we'll take it out, and we have a rework table over here to the side where I will take out the lead, and I'll go in and on the prongs of the actual stator, we'll test those to figure out if it was a lead problem or a stator problem. And once we figure out where the problem lies, we will then take it, resend it through our tanking process, repressurize it to tank it again to see if it passes. And if it doesn't, we send it to quality to be reworked.
Sounds good. That's a good thing right there. That's why we check every one of them. If we didn't check every one of them, that one could have, if it would have gotten put on a pump end and tested with a pump end, we would have caught it on the submersible assembly line. But if it would have gotten put into a box and sold as a motor on its own, you'd have had a bad motor right out of the box. So perfect reason why we check every one. Thank you for that, Shelby. Okay, so I think that kind of wraps it up. Thank you, Shelby, for taking the time to show us what you do. Thanks for everything you're doing here to make sure we're putting out a quality product. Let's go ahead and check back in with Dan, see if we've got all his bases covered. How'd we do there, Dan?
You both did great. I did want to add something that customers ask me. Sometimes I get asked, you said, hey, this will go all the way down into the copper windings in the motor? Yes, that's where it goes. And they asked me, they said, well, is that copper wire and that magnetic wire the same? And the answer is no, it's not. We use magnetic wire here in the manufacturing of our motors at Flint Walling, and that magnetic wire, as I mentioned a few minutes ago, has a thin film of insulation over it. And that insulation is very, very important. It bonds the wires together so they're not prematurely vibrating and wearing that insulation thin. So it'll go all the way down to there. So it's magnetic wire that we use.
Okay, all right, thanks, Dan. We'll wrap it up down here. All right, so just to recap everything we've done today. So we're in our 4-inch submersible motor manufacturing facility here in Kendallville, Indiana. We've got a chance to talk with Shelby, and we're looking at what we're doing at the end of our assembly process on our 4-inch motors. We're looking primarily here at our testing. So to recap that, we're putting every single motor into a pressure tank for a pressure test. They're sitting in that tank for 2 hours with 100 pounds of external pressure. We're trying to mimic their conditions in the well. Then we're going to check every lead with a Megger to make sure that our insulation resistance is good. We don't have any water intrusion into the lead socket, no water intrusion into the motor via the welds or anything like that. Again, if you have not been here to come see our process and see what we're doing, our 100% factory testing, we'd love to have you. If you have any questions, you can call me anytime, call your salesman anytime, or visit us at flintandwalling.com.
So good or bad, this is an industry standard, and so I'm going to throw this up here. These are not our numbers. These are industry standard numbers. We talked about with the multimeters, there were these resistance values that we published values that we were looking for. So with a megometer, it's similar, but perhaps more simple than that. Here's where we're going with that. If it's in the well, that's what we need to know. Is the motor in the well or is it out of the well? The second thing we want to know, is it a new motor or is it a used motor? All right, that's all we need to know. Is it in the well or out of the well? Is it new or is it used? So, for example, if it were in the well and it were a brand new motor, and you put your megometer on up there at the top of that well, you're now testing that resistance, all that electrical power cable running down to that pump motor. And so therefore, you need to be looking at 2 megs or more. If it's a used motor, it drops down to a 0.5 meg or more. Now these values come up significantly if you pull this pump and motor out of the well and you're testing this thing out of the well. If it's a brand new motor out of the well, you should be coming in at 20 megs or more. And if it's a used motor out of the well, that's 10 megs or more. Now, these are industry standards. These are industry thresholds. And the reason that they put these out as thresholds is for this. If you do a test and you come in lower than any of those values, any of them, do not reinstall that pump and motor because it's either dead or it's dying. So those are the values that we're going to stick with to determine whether we put a motor back in a well or not. Motors of all horsepower, voltage, and phase will have very similar resistance values. So unlike the multimeter, I really don't care whether what the horsepower is or whether it's a single phase or a 3-phase, because when we're testing for resistance values, those are all going to be very, very similar. And the last thing I would point out is that if you ever do test this motor and it's out of the well, make sure that it's sitting on a non-conductive surface. I'd like to thank you for watching this video. If you found value in it, please give us a like and subscribe to our channel. You'll also find an abundance of Flint Walling training videos on social media such as Facebook, Instagram, and YouTube. We actually have our own YouTube channel out there, and there's a lot of resources there for you as well. Thank you very much.